Hey guys, Mr. Butts here. I want to talk to you about a few related things, and this video is going to be pretty definition and theorem heavy, and you can refer to the next video and the next couple of topics to see how we're going to apply these ideas. So let's start with the definitions of global maximum and global minimum. So first of all, I want to point out that we will interchangeably use the words global and absolute when we're talking about these things. Um, so uh, a global maximum is going to be basically the largest value of a function over some interval. So if you look at the graph I have over here on the right, we have a peak here. That's going to be something we're going to talk about later. That's a local maximum, but the absolute highest value of the function is going to be at this point right here. So the value that we get at that point is the global maximum. On the other hand, the global minimum is the absolute smallest value that we get, or lowest value, and that's going to be at that point right there. So the definition looks a little formal. It says if f of c is greater than or equal to f of x for all x in the interval, then f of c is a global maximum. So what that says is if this y value here is bigger than or at least equal to any other value of the function on the interval, then we're going to call that a global maximum. So global, absolute, those mean the same thing. I also want to point out that the plural for maximum is maxima, and the plural for minimum is minima. So just recognize those terms when we see them. Another term that I'm going to use is extreme, or plural is extrema, and that's just a general term for maximums and minimums. A maximum is an extreme value, a minimum is an extreme value, and together they are extrema. That's going to be the plural. So our first theorem here is called the extreme value theorem. Kind of like the mean value theorem, this is what's called an existence theorem. It tells us that something has to exist under certain circumstances, and those circumstances are simply that a function is continuous on a closed interval. Both of those things are important, and I'll talk about why in a moment. But if a function is continuous on a closed interval, then f has to have a global maximum and a global minimum at some point on the interval. So it's not possible that we don't have an absolute maximum or an absolute minimum as long as those two conditions are met. So let's kind of talk about a few things here. One is, can there be more than one? So if we have on a closed interval, let's say we have something that looks like that, that's going to have one minimum and one maximum. But it is possible to have more than one. So just to give you a real simple example here, in this case, the endpoints are both absolute maximums. So we can have more than one. And we could even have a function that looks something like this, might be a sine function or cosine function, that has multiple. It's even possible that if the function looks like this, it has infinitely many. So if the function is a horizontal line on the closed interval, then every point on that line is both the absolute maximum and also the absolute minimum. So it is possible to have more than one and even infinitely many, but the extreme value theorem guarantees at least one. Next question, does it have to be differentiable? And the answer to this is no. So if we have a function on a closed interval, we can have corners, we can have cusps, we can have vertical tangents, and none of those really matter. So we have a corner there, kind of looks like. We have maybe a vertical tangent here at this point. The only thing that matters is that it's continuous on a closed interval, and in that case, it has to have an absolute maximum, looks like it's going to be right there, and an absolute minimum looks like it's going to be right there. Next question, why does it have to be a closed interval? I'm going to give you a fairly straightforward picture here and talk about why it needs to be a closed interval. So let's say it's an open interval on just a line that has some positive slope, and we want to know where is the absolute maximum. Let's say I pick a point really close to the end here. Since it's an open interval, I can always get a point that's a little bit closer. So if I get closer to that right end point, it's going to be a little bit bigger. So let's say this y value here is, I'm going to say f of b equals 2. Let's say the y value there is 2, and I pick a point where the y value here is 1.9. Well, I can pick one closer that is 1.99 by moving a little bit closer, and I can go 1.999. I can never get to 2, but I can always pick a number that's closer to 2 than any number that I pick below it. So this does not have an absolute maximum because there is no biggest value on the interval. Likewise, if we go to the left on this one, we can see that it wouldn't have an absolute minimum for the same reason. Next question, why does it have to be continuous? Well, let's draw another picture here, and this would be a counterexample to saying that it has or it doesn't have to be continuous. And I'm going to draw one with an asymptote in here. In fact, I'm going to make the function defined at every point. So if I wanted to know what is the absolute maximum of this function, kind of the same idea as I had approaching the endpoint on the last example, if I pick a point here that's pretty high, I can always get a little bit bigger by getting a little bit closer to that asymptote. So no matter where I am there, I can get higher and higher and higher as that function gets closer and closer to the asymptote. So there is no absolute maximum value. No matter how high I get, I can always get higher. So there is no absolute maximum. Had I left this an open point here, this function would also not have an absolute minimum. So just to give you another example here, let's just say the function looks like this. This function does not have an absolute minimum because no matter how close I get to this point here, I'm going to get lower and lower and lower as I pick points that are closer and closer and closer. And I can never actually get to that value. So there is no absolute minimum. Next question, can the functions have global extrema if the conditions aren't met? So if it's not continuous or not on a closed interval. So let's look at an example here. I'll give a pretty simple one. So let's say it's not a closed interval. So I'm going to give open endpoints, and it's not continuous. So this example right here, I think it's pretty clear that we have an absolute minimum. This is the smallest value of the function over the entire interval. And then right here, we're going to have an absolute maximum that's higher than any other point on the interval. So we can have these global extrema. It's not guaranteed if those conditions aren't met. So if a function is continuous on a closed interval, we have to. If it's not, we could still have them, but we're not guaranteed that we're going to have them. Okay, a couple more definitions here. We talked about global extrema. Now we're going to talk about local extrema. So a local maximum is essentially what happens if we just look at a neighborhood on a function and what is the biggest point on that neighborhood. So the definition we're going to use is, again, kind of formal. And it says if there is an open interval. So notice that the picture that I have here has these open endpoints. This could be a subset, a small part of a function that does continue beyond. We don't know what that function might look like. Let's say it goes down like this. But if there is an open interval for the function that contains a point where this same inequality that we looked at for the absolute extrema, if that inequality is still true, then the point is going to be called a local maximum. So even if you may have noticed when I continued this function, I went up like this, even if the function gets bigger somewhere else, within this neighborhood right here, it is the highest point. That's going to be a local maximum, or like we had with global and absolute, we're going to interchangeably use local and relative. Traditionally, local and global are used together. Absolute and relative are used together. But just make sure you know what both of those mean. And then the definition for local minimum is the same, but just flipped. So let's talk about closed intervals. So in this example right here, this function is going to have a local minimum at a point right around here, because if we just focus on some neighborhood, really doesn't matter how big or small the neighborhood is, that's going to be the smallest value around. But if we look at an endpoint, let's say this endpoint right here, can that be a local maximum in this case? And it depends on how we define it. So the definition that we have here says that C, and this is going to be our C value in this case, has to be on an open interval. Well, C cannot be on an open interval if it's an endpoint on a closed interval, because we can't have the left endpoint open to the left of this because there is nothing to the left of it. So if we redefine this slightly to include endpoints, we might just say that at the endpoint it can be a closed interval at the endpoint. It really depends on the textbook you look at. The AP curriculum, you can go either way, which I know sounds kind of annoying, but they don't tend to ask questions about endpoints and local extrema. But I would consider this to be a local maximum because it is higher than all the other values of the function around it. And the same thing over here, I would consider that to be a local maximum. So it really doesn't matter how we define it. Strictly going off of the definition that I gave you here, that technically would not be a local maximum. But if we allow the endpoint to be part of a closed interval in this definition instead of open, then we can include it. So I will generally call it a local maximum or a local minimum at an endpoint, but it really doesn't matter if we do or not. So I want to give kind of a real life example. If you look at the mountains behind me here, it looks like this point right here is the highest point in the picture. So that looks like a maximum value to me, a maximum elevation in this case. But if I expand the picture, we can see that this point here has a point that is higher than it over here. So even though this point over here is higher, this is still a local maximum. It's still the highest point around. In fact, if we look at this picture, there's lots of local maximums. Here's another peak right here that we would call a local maximum. Here's another peak right here that we would call a local maximum. We might even pick a point somewhere down here in the valley as a local minimum. So all of these points here are local maximums. And then if we want to talk about global maximums, we're looking for the highest point out of all of them. So in this picture right here, the global maximum is going to be here at the top of Half Dome. So a critical number, a number on a function, and notice that it says f of c is defined where the derivative is either equal to 0 or the derivative doesn't exist. So it's not differentiable at that point. If that's the case, so the function is defined at the point, but the derivative equals 0 or it is not defined, then c is a critical number. And the way we find critical numbers is we take the derivative of the function, we set the derivative equal to 0, we see where we can't take the derivative, we confirm that the function exists at those points, and those are going to be our critical numbers. So I will use the term critical number or critical value interchangeably. Okay, so in this case, we're just, when we say critical number or critical value, we're looking for the x value. And then I will also use the term critical point. And a critical point is the literal point on the function. So c is a critical number or a critical value. And so f of c is going to be the coordinates of a critical point. One more theorem. This one's an unnamed theorem. So the theorem says if f has a relative minimum or a relative maximum at some point in an open interval, then c has to be a critical number of f. So what that means is if we look at this graph here, this point is a local minimum. It's also, in fact, a global minimum. That doesn't really matter. So since that's a global minimum, that has to be a critical point. And indeed, if you look at it closely, you can see that it's going to have a horizontal tangent there. This point is a local maximum. And at that point, the derivative is not defined because we have that corner there. So anywhere that we have a local minimum or a local maximum, that point on the function has to be a critical value or at a critical point. Okay, so the big ideas here. One, the extreme value theorem. If a function is continuous on a closed interval, then it must have an absolute maximum and an absolute minimum on the interval. And then second, this unnamed theorem. If a function has a local extreme at a point, then that point must be a critical value. You might think that these two look like they could be connected, and they are. So we're talking about if a function is continuous, then it has to have an absolute maximum and minimum. If we have local extrema, then it has to be critical values. So we do need to make a connection between local extrema and absolute extrema. And with that connection in the next unit, we're going to be able to put these two together into a process for finding the values given by this extreme value theorem.